Hello students, in today's video we're going to be going over related rates, so let's get started. Go ahead and try this warm-up problem and come back and check your answer. Hopefully you've paused your screen and you're just coming back to check your answer. Question here says write a differential formula that estimates the change in volume of a sphere when the radius changes from r to r plus dr. So let's go ahead and consider the volume of a sphere is equal to 4/3 pi r cubed. Then we're going to go ahead and find the derivative of the volume. So volume prime is equal to 4 pi r squared dr. Now keep in mind, now that we're finding these differentials, you want to make sure that you add this dr at the end because we found the derivative with respect to r, which makes these even more important to us now. So as we go through, we're going to go ahead and start substituting now. So we know that it changed from r to dr. So this r would have been replaced with this r squared. And this dr, the dr, remember, is delta r, or the change in r. It changed from dr to dr. So just to make sure we clarify this a little bit, if we had from a to a plus dA, this would change to the following items. So notice the r's changed to a's, and then the a plus dA portion, that difference was dA. So that's why the dr became dA. So let's work on another problem. So we're going to look at related rates today. Now a rate, just to remind you, is a ratio of the change in one variable to the change in another variable. Typically the second variable is time t. Related rates are two or more rates that can be related in a single equation. So it's very similar to the equations that we've been working on, or the problems we've been working on over the last couple days. So example 1 says sand falls from a conveyor belt at a rate of 10 meters cubed per minute onto the top of a conical pile. The height of the pile is always 3/8 of the base diameter. How fast are A, the height, and B, the radius, changing when the pile is 4 meters high? Give your answers in centimeters per minute. So consider for just a second when we do these graphs, what we're really looking at here is a cone, because it says conical. So we have a cone like so, because sand is dropping into it. Now it says volume, so there's a couple things we need to consider. We know that the volume is equal to 1/3 pi r squared h. So this is the volume for any cone. The other thing they mention is that the height is h, is equal, height is 3/8 the base diameter. So 3/8 d, or 3/8 times 2r, because the diameter is equal to 2 times the radius. And finally 3/4 r is our most simplified version of that. So now what we're going to do here is we're going to go ahead and replace some things. So what we're going to go ahead and do is replace the radius, because we wanted to find everything in terms of h, because part A says find the radius, or find how fast the height is changing. So taking this second equation here, we're going to find that r is equal to 4/3 h. So now we know what r is equal to. Now we're going to substitute that into our volume formula. So volume is equal to 1/3 pi 4/3 h quantity squared times h. Notice we replaced the radius with 4/3 h. We're going to be left with v equals 1/3 pi times 16/9 h squared h. And finally, v is equal to 16/27 pi times h cubed. Finally, we want to find this change, this rate of change. So we're going to have to find the derivative here. So v prime is equal to 16/9 pi h squared. So that's the derivative of this. Oh, we forgot to put the dh. Remember, dh is really important now that we're finding derivatives and substituting things in. So we're going to make one extra change to make sure we understand things. Remember, the v prime is your change in volume. It gives you your rate. It gives you how fast something's changing. So we're going to change this to dv dt. And while we're at it, we're going to change this dh to dh dt, because as it changed with respect to time. So we know that dv dt, based on our problem, is 10, because it's 10 meters cubed per minute, equal to 16/9 times h squared. Well, h we're not exactly sure of, right? Or we are. Because if you look at part B, it says the radius is changing when the pile is 4 meters high. So we do know h, and that's 4 squared, times dh dt. Now solving for dh dt, we get dh dt to be equal to 45/128. But keep in mind this is meters per minute. So this is meters per minute, and we are supposed to put this in terms of centimeters per minute. So what we're going to do here is we are going to, because the meters is on top, we're going to use a little dimensional analysis and multiply by 100 centimeters divided by 1 meter. dh dt is going to simplify to, oh, my apologies, this is 45/128 pi. And then dh dt is going to be equal to 1125 divided by 32 pi, which is approximately 11.19 centimeters per minute. So now that we know the rate of change for the height, we're going to go ahead and find how that affects the rate, or the radius. So we know originally that r is equal to 4/3 h. If we find the derivative, we have dr dt equals 4/3 dh dt, because we found the derivative of h. We don't know dr dt, that's what we're trying to figure out. We do know 4/3, and dh dt we just figured out was 11.19. So we know the change in radius is 14.92 centimeters per minute. So let's give you a couple steps that might make this easier. Step 1, you want to draw a picture and name the variables and constants. 2, you want to write down the numerical information. 3, you want to write down what we were asked to find. 4, write a single equation that relates the variables. 5, differentiate with respect to t. And 6, evaluate. So let's look at another problem here. It says a balloon is rising. A balloon is rising vertically above a level, straight road, at a constant rate of 1 foot per second. So here's our balloon rising. Just when the balloon is 65 feet above the ground, a bicycle moving at a constant rate of 17 feet per second passes under it. How fast is the distance between the bicycle and the balloon increasing 3 seconds later? So, as we go through this problem, there's a couple things to consider. 1, this thing is rising at 1 foot per second. So we know that dy dt is equal to 1. We know that dx dt is equal to 17 because the bicycle is moving at a rate of 17 feet per second. We know that our initial height is 65, and we know that our initial distance for the bike is 0. Now, if we take into consideration the balloon, or how fast is the distance between the bicycle and the balloon increasing 3 seconds later, we need to change that time a little bit, or that y. So that y is now going to be y plus 3. And the reason why it's 3 is because the constant rate is 1 foot per second. So 1 foot per second times 3 is 3 seconds. Therefore, that initial height is 68. And we know that at x equals 0, that's when the bike just started moving. The rate is 17 feet per second. So after 17 seconds, or after 3 seconds times 17, we get 51. Now I'm sure you all noticed that this was a right triangle that was drawn. So what we really have here is S, which is the hypotenuse. We have y and x here. So we know that s squared is equal to x squared plus y squared because of Pythagorean theorem. We know that s is equal to the square root of x squared plus y squared. We know now that here's the formula. So what we're going to do here is we're going to find the derivative. So we know that ds dt is equal to 1 divided by the square root of x squared plus y squared. And furthermore, because we're doing this as chain rule, then we know that we have to find the derivative of the inside of the parentheses. So that'll be dx times dx dt plus 2y dy dt. So I'm going to move our formulas over a little bit. So now we're looking at the following equation, like so. And now we're just simplifying, or we're substituting things in. So we know that ds dt is equal to 1. Oh, I forgot. When we did this derivative, we had to do a 2 down here also because it became 1/2. So now we're simplifying things. We're going to throw in 1 divided by 2 times square root. X became 51 squared plus 68 squared. And then we have this 2x dx dt business. So I'm going to go ahead and write that to the right because we're multiplying 2 times 51 dx dt, so that's 17, plus 2 times y, which is 68, dy dt, which is 1, and when you simplify all of this, you get ds dt is equal to 11 feet per second. And that's it. Last but not least, this one should be a little bit easier to see. We have a spherical balloon. The air pump delivers a constant rate of 12 centimeters cubed per second. So notice they gave you a changing volume here. So we know that the volume of a balloon, which is spherical, is 4/3 pi r squared h. Oh, my bad. Pi r cubed. Forgot it was a sphere. Now we're going to go ahead and find the derivative here. So dv dt is equal to 4 pi r squared dr dt. Now they already gave us that dv dt. They said that was 12 equals 4 pi. And then they said the radius was 8. So 8 squared dr dt. And then when we solve for dr dt, we get 3 pi divided by 64. So that's all for now. You'll have plenty of time to practice in class. But that's all for now. I'll see you guys next time.